Hello? Hi. Good morning, ladies and gentlemen. My name is Lily, and this is my coworker, Christian. We both are from D2L. Today, we're really honored that we're given this opportunity to share the lessons and basically the pitfalls and everything that we learned for building serverless applications with the community. And before we start this talk, okay, so the other two speakers this morning told you how nice serverless is going to, help you build your business applications. With this title, you might say, hey, yeah, nothing is perfect. We're going to tell you something that you still need to take care of, the bad things. To start with talk, I want to ask a couple questions. So in the audience, if you ever built any applications, you think that the requests that the application receives are actually exceeds what the application can handle. Has anybody built any application like that? Well, quite a few. And even if you don't just take directly like requests like that, maybe you are building a service that is calling your dependent service, and you might have injected too many requests and maybe even bring down the next service. Have you ever built something like that? Thank you. Actually, me too. So if you ever experience that, you probably know what happens. Either the request might get slowed down and really, really bad, performance, or worse, sometimes the system completely just break down and became unavailable, right? So basically, today we're going to just to tackle this kind of a problem. How do we build scalable systems? And first, we're going to have a very, very brief introduction about D2L. This is a company that builds integrated learning platform for our customers as a service. And our hope, our vision is to help the world to change the way we learn. I still remember about 5 years ago when I joined the company. At that time, we still had data centers. So across the world, different data centers. We are totally in control of all the hardware, web servers, databases, networking, and disks, everything. So what is really a big thing for the company is capacity planning, specifically during the semester start time, when all the students came back to school and everybody get on the system. And that is when the load sometimes surge, and we have to make sure that our customers are happy. So how do we do that? We want to make sure we have enough hardware resources to handle them. However, by doing this, what do we have to do? There are a lot of work, preparation, right? We have to monitor and then try to predict what kind of traffic pattern is, what kind of predict the load we will have, and then predict how much hardware web server we should set up in the pool. And in the end, what ended up happening? Two things. Usually, we either overestimate and then we set up a lot of hardware out there, just wasting money day by day without really much load there, or we underestimate. In that case, we will have talented developers spending time in a war room and putting out fires. So this is really not working out for our company. So our company has set out, say, no, this is not good. We need to really build something that is scalable and resilient. What does that mean? So first, it has to be horizontally scalable. And the system should not really fail that easily and reach its capacity when our users grow. Second, it has to be cost efficient. So this has two meanings. One, of course, you don't want to set up a lot of hardware when you don't have to use them. So that's elasticity you need to. And also, you don't really want to spend so much time to do DevOps, right? To do a lot of things like when things not working, you have to do maintenance manually. That's manual work is what we don't want. The third is, of course, it needs to be resilient for traffic spikes, for surges, and for partial system failure. Last but not least, most importantly, we need to make sure that our customers are happy. That means we have to keep the low latency even when our customer base grows. So with this in mind, fortunately, AWS provided a lot of the features that we will need. Elasticity is there. And so we actually moved from the old monolith system, which are built on our data center, into AWS, and then try to develop a new microservice architecture. In particular, about a couple of years ago, we started even to take advantage of the serverless technology. It actually really released us from a lot of the trouble we had before, right? We don't have to really think, hey, it's like we don't really have to manage those servers anymore. We don't have to care that how many servers we have set up, because serverless, like vendors like AWS, they would actually scale our computer power on a dime very quickly. So a lot of people are very, very excited. Isn't that great? Now we can focus on developing the real business value, the APIs, right? However, while serverless did solve partially the problem of scaling hardware, it actually brings in more challenges that what we didn't really expect. One of the things is, when you think the compute power is expanded so quickly, the database side, data server, they do not really scale as quickly. Like say DynamoDB, if we use that as the backend, they do not scale like that. So what happens? Basically what happened is like you just pushed your bottleneck to the next hop. That becomes a huge challenge, because so over the last couple of years, what we found is different teams have developed applications in different architectures, using like maybe event-driven or not. But everywhere I see this problem happen again and again, that the system still fail, still not resilient. And the worst of all, it fails even earlier than before, much easier. Without even much load, it will do it. So today, in the rest of the talk, we're just going to share with you some of the pitfalls and the effort we did to how to improve this kind of a capacity management problems. So.
Hello. Good, you can hear me. I'm also really excited to be here. And in this talk, we're going to dive really deep into some practical examples. So we're going to actually build something together. And as Lily mentioned, we use AWS, but it should be applicable to Microsoft or to any other cloud provider. So as Keith mentioned, APIs are really central. So we picked that as our core example. But we should apply our ideas here to almost any system. So just in case you're not familiar, probably you know these services, but I'll just quickly introduce them. So API Gateway is an interface to invoke Lambda, because you can't call it directly from the internet. So we just put it there so it's publicly facing, and you can set things up like caching and authentication, but we're not going to use that. Then Lambda is our main compute power here. So we're going to act as the web server, basically. And this demo application is just going to write stuff into a database. Our database is going to be DynamoDB, and that's a NoSQL database. And it basically set a capacity. Actually, when we started using it, there was no auto-scaling. So you had to pick a number, the magic number. In this example, we're going to pick 20. That basically means we support 20 kilobytes per second. And the DynamoDB also supports spikes. So like if you actually don't use your capacity, it will actually let you go over that for a bit. And then you can, like when it goes down, it will still count as your normal usage. Right, so we're going to overload the system. And we want to really think deeply about what happens when you overload this, because we probably all think, oh, Lambda scales, it's great, it's going to magically work. But we're going to show in this talk that you still need to think about performance. You still need to think about what problems can you run into. And so basically what we're going to do is we're going to run load with artillery, is like a load generator. And it's going to start making some requests. And if Dynamo writes successfully, we're going to return right away. And if not, we're going to get some throttling, and Lambda might retry. We're just using the standard SDK. Okay, I hope you had enough coffee, because we're going to dive deep into some charts here. Let's talk about the scenario. Oh, I was told I'm not allowed to walk there, so I'm going to just have to explain it visually. So from 0 to 50 seconds, we're going to run normal load of 20 requests per second. So we should be able to handle that, right? And then after 50 seconds, for the rest of the experiment, we're going to run 100 requests per second. That's way more than Dynamo can handle for this capacity. And then what we're looking at here is the latency, the 95th percentile. And so low is good, high is bad. High is like 30 is the maximum that API gateway lets you do. So if you go higher than 30, it times out. For the rate, it's basically our throughput. So the blue line is our successful rate. So you can see in the beginning we start with 20. It's all good and nice. After 50 seconds, we ramp up the load. And wow, DynamoDB is actually taking the load as well because of the burst capacity, right? And after around 120 seconds, we see that Dynamo says, no, you're not paying for us. We'll stop taking that request. So we go back to 20, and latency goes up a lot. And the reason is because we keep retrying and retrying. And the SDK actually does many retries. So we get the red line, which is DynamoDB throttled us 10 times. The yellow line is timeout. So we kept retrying for over 30 seconds. And the interesting thing here that we did not necessarily expect was Lambda throttling. Why is Lambda throttling us? Like, it should just scale, right? I'm just going to flip over this chart here. Actually, the concurrency is really high. So we have 1,000 Lambdas running at the same time if we send 100 requests per second. That's because we're running for a long time, and they just don't finish running. And AWS has a default limit of 1,000. And you should realize that that's going to be expensive if we have always way too many CPUs running. And we also have other Lambdas in the system, so we don't want to overuse the concurrency. It's going to affect other systems. So this is not good. We have kind of an efficiency metric for every experiment we do. We're going to run other experiments. And basically what this number means is take all the latencies, and instead of averaging them, we're just going to count the successful ones. So take the total time spent and divide that by the number of successful requests. So we're actually spending 50 seconds for every request. That's not very efficient. Now, what can we do? Our database is, let's not think about auto-scaling and updating the database yet. We want to waste less money here. So what most of us at D2L do, and I suspect you would think of that too, is let's put some rate limit. Just keep in mind that the database could be some other system. It could be something that easily fails over if you overload it. Actually, that happened to us. And so we just thought, okay, let's put some rate limit, and then we're safe, right? So API Gateway supports a rate, and we can just set that up, and it works. So if we run this again, you can see the rate that goes through is steady, and after 50 seconds, we just reject early. So failing early is good. You can also see that we're not using the burst capacity here because we're nicely unsteady. Now we can all go home now, right?
That didn't really last that long. What happened is...
Wait.
Oh. You forgot about that. So maybe I'll explain this. Okay, this is the new efficiency that we calculated. So with this rate limiting, at least it's much happier because when we had no control, we had the efficiency of, we just call it 50, right, per each success. And with the rate limit, at least now it's only 1.3, so you actually saved 96.6%. So that's the efficiency increase. So it's not completely bad, right? With the rate limit, you do increase something. However, it does not always work. What we experienced was, very soon we found out, well, the traffic is not always steady, right? So when you actually rate limit, you actually assumes some steady average rate. In some ways, in our case, it's like, because each request, we say, okay, we think each request probably will be under 1 kbytes, which means when you write to DynamoDB, it is about 1 write capacity unit. That's why we set the rate. However, in reality, it's not always the case. We found that some of the requests, largely actually exceeded the payload we expected. And then, so in some cases, it's about like, it has a 10K bytes. That was unexpected. What happens when that happens? So we will show you by changing the scenario in the experiment to add 20% of the requests with 10 WCU. What happens?
Right. Did you ever get any unexpected traffic? Like, it happens, and it happens to us, and it's not good. You basically get high latency, and it's the same mess as before. Actually, the reason is because now if we average the number of capacity units we're using per request is higher, as instead of 1, we're going to 2.8. And this could happen for many reasons, right? It could be you change your application to write more to the database, or you just get some different traffic that you're not necessarily expecting. And the results here are basically, we're using up the burst capacity, and it actually takes longer to use up the burst because we're still rating, like rate limiting a little bit. And after we use the burst, things start to go as badly as before. So we go down the rate, which is the maximum for that type of load is around 7, and all the rest is going to be making the latency go high. So our successes are slower and our failures are slower. So this brings us back to 50 per second as an efficiency metric. So we're still wasting a lot of money. Time is money, right? As we know in Lambda. Yeah, so what can we do? Do you have any ideas?
So clearly, no control nor rate limiting actually works really well. So in this case, because when you have a surge of load, there is congestion problems. How do we really solve it? So before we really continue, I want to step back a bit. Think of this more generic capacity problem, because this is not really new in digital world. The capacity, everything has a limit in capacity. Physical world, that's just the law. And so, for example, if you want to go to a good restaurant at like maybe 7 o'clock at night, you probably will have to stay in line. Why? Because they don't have enough tables for you. And if you ever went to like the mall on the holidays, have you ever been to something like Boxing Day in Canada or Black Friday? Have you ever been the door crashers? You will see what happens. As soon as the door opens, people would just run in without any control, right? What happens? Sometimes, I do remember early on I did, and then you just, you couldn't find what you want, and you couldn't find any clerk. You still have to compete in the cashier. You just have a very, very, very bad experience, what I can say. So nowadays, I don't really go there anymore. For exactly that reason. However, I do remember some good experience too. I remember once that I went to some higher end stores where people really care about the customer service. So even during the holidays, I remember there was some guy that would be at the door of this store, stopping you because they say, we have to wait. Because in the store, they still just have a few customers. Every customer will get their good service from their clerk. And that's when do they allow people in? Is when some customer come out. So what they're actually controlling? Are they controlling the rate, saying, okay, every 2 minutes you can get into 10 people? They don't, because it depends on the customers. Some customer, they might want to spend a lot of time buying like $1,000 of goods. Why do you want other, customers to go in and disturb, right? So what they really control is the maximum people that are in the store at the same time. Or in digital world, what is that? Max concurrency. Isn't that interesting? I mean, this is so natural, so intuitive in the non-digital world. However, in our computer world, we don't seem to have applied that much. But how to apply it? This question is also interesting. You see this as I would say 60 years ago, John Little actually already solved the problem. He was the one that basically worked out the relationship for really capacity management. That is, the concurrency equals a product of the arrival rate multiplied by the latency. What does it mean? It's like exactly like in the store case. All the customers in that store, the store has the capacity, all the customers in the store, that on average, the number, what is it? It is, the rate that customers get in the store, that, the clerk allows you to get in, the rate on average, let's say maybe like 1 per minute or something, and then multiply by the total time on average, like each customer stays in the store. So this applies to all type of systems in our digital world. So in this case, this equation actually can tell you really well why the rate limiting didn't work. If you look at this simple like just now when we say, hey, you know what? We think our system can handle the rate of, like say, 20 per second. However, when it cannot, when somebody spends too much time on it, you can see the latency goes up. What happens? The left concurrency increases. That means you're going to increase the number of the requests, whatever, inside your system. In the end, it will be exceeding the total capacity, which is a concurrency, right? So on the other hand, if you actually fix the concurrency, what does it mean? You basically fix making sure nobody is going over the capacity limit. What happens when somebody really stays too long inside your system? Well, basically that means your throughput, your rate is lower. So it's kind of adaptive. That's why controlling concurrency is much better to adapt to a little bit dynamics of the system. So that sounds great. Why don't we do a concurrency limit and see whether or not that works?
Right. Is it still working? Good. Let's try to be a high-end store and be nice to our customers. So we'd like to remove the rate limit because that didn't seem to work. And let's forget about the new traffic pattern. We don't know about this. So we're just going to estimate what is our concurrency limit. So if we use Little's law, before we had a rate limit of 18 because we were conservative, we set it to 18. And we also measured a latency of half a second. And that gives us 10 concurrent requests. And you can also measure this. Like, it turns out the law is true. You can measure or calculate. So we just did both, and they were both 10. And so we're like, let's set it to 10. And now we run the same trouble as before. We get unexpected load. And what will happen? This is what happens. Looks a bit better. So even though we did not anticipate this traffic, concurrency limit seemed to be more flexible. It's not getting as high as latency as before. You can see we still use the burst. At the end, we go down, like we can't use more than 7 per second. That's our ideal number with fixed database. But as soon as the latencies went up, because we fixed N and not R, like the latencies went up, and therefore we're automatically gonna let less things in because we're fixing the number of things that are going on at the same time. And so instead of having a straight line, the purple line or pink line, we're actually rejecting more later. So first message here is use concurrency limit if you can. It works better and it's more flexible. So to compare numbers here, we went from 50 down to 3.8, even with unexpected traffic. And you save some money. Now, it turns out not every system is this simple. So you can spend as many nights as you want understanding your system, and you might still not get the right concurrency limit. So let's assume we just set the wrong number. We picked 50. So because we picked 50, we can use Little's law again there at the bottom. 50 concurrent requests, and assuming the same latency as before, now we're at 90 requests per second that we're doing to the database. That's way too much. So that gives you an idea that we're really misestimating the number. It shouldn't be this high. However, this is actually better than rate limiting. Even though it's completely wrong number, we are 9.5 and the rate limit was 50, right? So we're still doing that bit of flexible rate limiting. So we're stopping more requests than rate limiting would in this unexpected scenario. So even if you don't know your numbers, still use concurrency limit. We tried that, but however, it's not always possible. Systems are complicated. So when can you not use concurrency limits? Let's say you have two things writing to the database, and that's very often the case because we have an API above, and then we have some event-based system that reads from a queue. And let's say the queue is batched. So you're doing, let's say, 10 items at a time, and above you're just doing one at a time. So how do you manage the concurrency? Like, because a concurrency, like one concurrency for below means 10 things, and 1 unit of concurrency above means one thing. So there's just no way to control it centrally. Even if you did set it separately, you might be wasting your capacity because let's say your above system is idle, then you're only using 50% below. That's not good. More problems is you might add a new system, and now you have to recompute everything. You have to get all your architects and designers and people to reevaluate how you're gonna do safe limit here. And also something that Amazon introduced not too long ago is auto-scaling. So we want to use that. But if you have a fixed rate or a fixed concurrency, you're just not making use of it, right? So it seems like it's not going to work in this case.
Yeah, now I think I kind of understand why in digital world we are not that good at concurrency limit. It's not that the concurrency limit doesn't work, it's too complicated because the digital world has so many different factors that might change. In particular, after we have these cloud technologies that can have elasticity, and specifically with the serverless, you can instantly spin up all these lambdas, computer powers. These made the system even more dynamic than before. So that's why I think fixed concurrency limit calculation is not only not possible, but also it is just not going to adapt enough. We need a dynamic algorithm to deal with these kind of dynamic systems. Does that sound familiar? You have capacity problems, and you need a dynamic. Have you ever thought of a TCP? 40 years ago, TCP already solved this problem, even though it's in a different layer. So what they do is they have multiple TCP streams, right? And then you might have the same sink, but then different sources. And all these TCP streams, they don't even know each other. So it's like our distributed system. How do they control the capacity? they use the dynamic algorithms that is called additive increase, multiplicative decrease. What it means is, in general, it will be carefully probing the system and see, hey, do you have more capacity to use? If you do, I will try to adjust my concurrency limit dynamically so that I can take advantage of it. But then if I sense that there might be something going on there, either a loss or maybe too long a latency, I say, okay, there's a congestion, so I really aggressively decrease my concurrency limit so that I make the system, resolve its congestion problem. This is very interesting algorithm. Then, with our distributed system, we could definitely take advantage of this algorithm. So while we were thinking about it, it's very interestingly, we found an article on the website. Netflix already thought about it. They actually did exactly TCP-like algorithms that is based on latency detection. So with all these work, we were thinking, okay, maybe we can take advantage of what Netflix is doing and see if it will be able to help us.
Gonna skip ahead a few things here. So Netflix came up with this formula, and it's a really great idea. Basically, it's based on TCP Vegas that takes the latency, and if you're higher lane latency, we're gonna go down with your concurrency. So it's a really nice idea. However, it's not super straightforward to apply it to serverless. So if I move back a bit, we have the same setup, and we need to measure latency. So we need to have some sort of statistics gathering. It's either CloudWatch or you have your own custom server to collect those statistics. For this experiment, we were just publishing metrics to CloudWatch. And then we had a machine who would keep reading those metrics and evaluate that formula and update the maximum concurrency according to the formula. So we're now not dealing with one server or multiple servers and setting their concurrency inside the server. We're actually working with infrastructure. So I'm calling the AWS APIs, and we're updating the limit that AWS will let for the lambdas. Let's just briefly look at the formula. Basically, we have a way to multiplicatively increase and a way to, decrease. And then at the end, we have something to go up. So on every iteration, in this case, we did it every 5 seconds, we would measure the latency. So we have the latency with no load and the actual latency. And so if we have no overload in the system, this will be 1, right? Because it's the same. If we have a slow system, then it's going to be less than 1. So our limit is going to go down. We multiply by something less than 1, so the limit is going down. And if the system goes back to normal, this will be 1, and then we'll go up with the last term there, the square root of the current limit. The square root lets you grow faster when you're in lower numbers and be a bit more stable in higher numbers. We did not experiment too much with having different numbers there, but that seemed to work. Different operations, but the square root seemed to work well for us. So how well? This is how it behaved. So we absolutely set no limits in advance. We just let the system figure it out. So in the beginning, it used up all the bursts. You can see from 0 to about 10 seconds, the blue line used up the entire burst right away. And after the burst capacity was over, it started rejecting us. You can see the red line in the latency. And we also started getting slower responses, and therefore the algorithm figured out that it needs to update the limit to be lower and lower and lower, and at some point we were rejecting most requests. And after a while, we're actually better than the perfectly set rate limit or concurrency limit. It just adapted. So it took a little bit, like the challenge is the detection, right? So those peaks you see there are because the timeouts are so high that we need to wait for this long to detect. But still, after detecting, fairly quickly we went down to the right rate. So yeah, I just wanted to mention that this is pretty experimental. Like, we have not yet added the dynamic version to our systems, but we're considering it. And if you have done something like that, please come talk to us, especially if you've done it in serverless. We also done some experiments with DynamoDB autoscaling. So for free, now we can just add autoscaling, and you don't have to change anything. So I'm not going to go into details here, but basically you can see the blue line goes up. That means we're accepting more requests because Dynamo scaled. And remember that if you don't use this, it takes time to scale. Like, actually, in this case, it was one of the quickest times I saw for our experiment. It scaled in, what, like 2 minutes? It can take 20 minutes sometimes to scale. And what do you do until you scale is really important. You need to reject early. And if you don't use any limit, even if you think I'm going to auto-scale at some point, you're going to have a terrible experience in those 20 minutes and lots of support calls. So yeah, dynamic concurrency works, but it's experimental. And our efficiency metric is also much better because we're now servicing more successful requests.
Okay, before we end our journey today, I think it's a lot of talk. There are only 3 things you really need to remember before you walk out of here. So the first thing is, for capacity management, concurrency limit is better than rate limiting. That's the first thing to remember. Second, in general, I would say for the static rate limiting that we did, you could see that in many cases, they actually were pretty good. So when you actually just starting a new service and stuff, when the things are not that complicated, that it's easy to do the calculation, what kind of concurrency should be good, just do it. At least it will give you the benefits. And as soon as you have a lot of services, system becomes so complicated, it would be almost impossible to do that. In that case, do consider the dynamic concurrency limit. It is not really easy. We're still doing research on it. And so that's why, that's probably secondary that you should consider. And the third, but not the least, is the Little's Law. It's a very simple equation. However, it is so powerful. So do use it. It will help you to identify when you have problems in scalability, where the problem is, and it will help you to calculate how you can fix your system efficiently. So those are the 3 things that we really want to tell you.
Right, I'll be quick here because we want to have some time for questions, but some small things that we found useful, and hopefully you might find them too. The retry strategy is really important. If we had time, we could have 10 more charts about retries, and depending on your system, the default might not be what you want. So the default for the SDK is 10 times, and that's over 30 seconds. And you want to fail early. Like, if you know that you can't handle it, don't keep retrying. Like, it's going to make the detection really harder, and it's going to make everyone suffer by having high latencies. So think about where in your system of microservices are you retrying. And it's not an easy, there's no easy answer, but think about it. The other thing is concurrency limit per lambda. If you're doing, let's say, a batch, and you set a fixed limit just to be safe. We did that, and we still broke our system. And it's because there's actually no limit. So if you're scaling your lambda and every lambda has a fixed limit, there's still no limit. So just think about your actual concurrency limits in the end. And last but not least, never think your system is fully scalable and just because you're using serverless, you don't need to worry about it. Always load test. Like, we ran into many silly issues where we thought on paper we were so awesome, but then we only had 10 per second maximum, and it was something silly, but you have to load test your system before you can claim that you're scalable.
Okay, so thank you very much, everybody, to listen to our talk. And I wonder